Hi everyone. In this video, we are going to discuss sodium dodecyl sulfate polyacrylamide gel electrophoresis SDS-PAGE. Before I dive into the topic, I request you guys to please subscribe to my channel for videos on fundamental of proteomics and share the videos so others can also benefit from it. Okay, now let's go back to SDS-PAGE. When I started my lab work, I was very fascinated by electrophoresis. And yes, that's me loading the samples onto the acrylamide gel. I'm sure you know that when a charged molecule placed in the electric field that exists between two electrodes immersed in the solution, it migrates toward one electrode or the other. Molecules with a net positive charge migrate towards negative cathode, whereas those with a net negative charge move towards the positive anode, and this migration is called as electrophoresis. I think SDS-PAGE is amazing the way it separates proteins based on their molecular size. Since the method is based on the separation of the proteins according to size, the method can also be used to determine the relative molecular mass of proteins. How? We will see later in this video. Let's start with the preparation of polyacrylamide gel. The polyacrylamide gel is a cross-linked mixture of polymerized acrylamide and bisacrylamide. Just note that bisacrylamide is two acrylamide molecules linked by a methylene group and is used as a cross-linking agent. When you start casting a gel, acrylamide monomer is polymerized in head-to-tail fashion into long chains, as you see here, and a bisacrylamide molecule is built into the growing chain and thus introducing a second site for chain extension. Proceeding in this way, a cross-linked matrix of well-defined structure is formed. So now, if you are curious enough, you may question how the polymerization occurs. Well, the polymerization of acrylamide is an example of free radical catalysis, and it is initiated by the addition of ammonium persulfate and the base tetramethylene diamine, TAMID. TAMID catalyzes the decomposition of the persulfate ion to give a free radical. I'm sure you know what is a free radical, right? A molecule with an unpaired electron. Look at the reaction where persulfate is catalyzed by TAMID, resulting into a free radical SO4-. If this free radical is represented as R dot and M as an acrylamide monomer molecule, then the polymerization can be represented as shown here: R dot plus M, RM dot, RM dot plus M, RMM dot, and so forth. In this way, long chain of acrylamide are built up, being cross-linked by the introduction of the occasional bisacrylamide molecule into the growing chain. Oxygen mops up or removes free radicals, and therefore the gel mixture is normally degassed prior to addition of the catalyst. So now you know, to cast a gel, we need acrylamide, bisacrylamide, APS, TAMID, and buffer to maintain pH. In this case, trace HCl buffer pH 8.8. You can prepare stock of acrylamide solution, 30% acrylamide and 0.8% bisacrylamide. Filter through Wattman number 1 filter paper and store at 4 degrees Celsius. Since acrylamide is a potential neurotoxin, you should be very careful, especially when weighing out acrylamide. Do this in fume hood and wear an appropriate face mask. However, nowadays most of the laboratories use the ready-made acrylamide solution 40% or 30%. Once you have a stock acrylamide solution ready, you can prepare 10% SDS, 1.8 molar trace HCl, pH 8.8 and 10% ammonium persulfate. Make sure you prepare APS fresh every time you cast a gel. To cast 15% or 10% separating gel, mix the ingredients as shown in the table up to APS. Degas this solution under vacuum for about 30 seconds. After that, add 14 microliter of TAMID and mix evenly. The addition of TAMID will initiate the polymerization reaction. Usually it takes 15 minutes for the gel to set, however, this time can vary depending on the room temperature, so it is advisable to work fairly quickly at this stage. Using a pipette, fully transfer this separating gel mixture to the gel cassette between the glass plates, keeping 1 cm free on the top. Once this is completed, you will find excess gel solution remaining in your flask. Dispose of this in an appropriate waste container and not down the sink. To make sure that the gel sets with a smooth surface, I usually add around 200 microliter of distilled water on top of the gel. Because of the difference in the density, water will spread across the surface of the gel without serious mixing. Some people add a water immiscible organic solvent such as isobutanol to the top of the gel. Once that is done, now you can let the gel set. Once the gel is polymerized, you may apply the samples directly to the top of the gel. This gel is called as separating gel. However, in this case, the separated bands will be broad due to diffusion and sharpness of the protein bands will be reduced. Basically, for some work, this may be acceptable, but it's nice if we get better resolution. You can achieve this by polymerizing a short stacking gel on top of the separating gel. The purpose of this stacking gel is to concentrate the protein sample into a sharp band before it enters the main separating gel, and hence this results into sharper protein bands in the separating gel. And most importantly, this allows relatively large sample volumes to be applied to the gel without any loss of resolution. The stacking gel has a very large pore size, usually 4% acrylamide, which allows the protein to move freely and concentrate or stack under the effect of electric field. Sample concentration is produced by isotachophoresis of the sample in the stacking gel. I will explain you isotachophoresis later in this video. While the separating gel is setting, you can prepare the stacking gel solution by mixing the ingredients shown in the table until APS. Degas the solution as before. When the separating gel has set, pour off the overlaying water, add 14 microliter of Temade to the stacking gel solution, and then add the stacking gel solution on top of the separating gel until the solution reaches to the edges of the gel plates. Place the well-forming comb into this solution and let it set. This will take about 20 minutes. Once the gel is set, carefully remove the comb from the stacking gel and assemble the cassette in the electrophoresis tank and look for any leaks. So, in short, the proteins migrate first into a stacking gel with neutral pH in which they are concentrated, and then they migrate into a separating gel with basic pH in which the actual separation takes place. Stacking and separating gels differ by different pore size, ionic strength and pH values as shown in the table. Samples to be run on SDS-PAGE are first boiled for 5 minutes in sample buffer containing beta-mercaptoethanol or DTT, dithiothretol, and SDS. The mercaptoethanol or DTT reduces any disulfide bridges present that are holding together the protein tertiary structure. SDS is an anionic detergent and binds strongly to the protein and denatures the protein. Each protein in the mixture is therefore fully denatured by this treatment and opens up into a rod-shaped structure with a series of negatively charged SDS molecules along the polypeptide chain. On average, one SDS molecule binds for every 2 amino acid residues. The original native charge on the molecule is therefore completely swamped by the SDS molecules. The sample buffer also contains an ionizable tracking dye, usually bromophenol blue, that allows the electrophoretic run to be monitored. Due to the relatively small molecular size of bromophenol blue, it migrates faster than proteins. Sucrose or glycerol, which gives the sample solution density, thus allowing the sample to settle easily through the electrophoretic buffer to the bottom when injected into the loading well. So now we know we need SDS, sucrose or glycerol, not both together, beta-mercaptoethanol or DTT, bromophenol blue and buffer 0.6 molar tris HCl pH 6.8 to prepare a sample buffer. And this is how I boil the samples in Eppendorf tubes on a heat block. The temperature can be set in the range of 80 to 100 degrees Celsius. Now prepare electrophoresis running buffer as shown in the table using trace, glycine and SDS. Make up to 2 liters with water. No pH adjustment is necessary. The band sharpening effect, isotachophoresis, relies on the fact that at neutral pH, glycines in buffer predominantly form the Zwitter ionic form. At high pH, the glycines lose positive charges and become predominantly anionic. In the stacking gel, the smaller negatively charged chloride ions migrate in front of the proteins and the slightly larger negatively and partially positively charged glycinate ions migrate behind the proteins. Whereas in the comparatively basic separating gel, both ions, chloride and glycinate, migrate in front of the proteins, and this is called as isotachophoresis. Once all samples are loaded, a current is passed, usually a voltage around 100 to 150 volt is applied, which causes a migration of negatively charged molecules through the gel in the direction of the positively charged anode. Once the protein samples have passed through the stacking gel and have entered the separating gel, the negatively charged protein SDS complexes continue to move toward the anode, and because they have the same charge per unit length, they travel into the separating gel under the applied electric field with the same mobility. However, as they pass through the separating gel, the gel acts like a sieve. Small proteins migrate relatively easily through the mesh of the gel, while larger proteins are more likely to be retained and thereby migrate more slowly through the gel, and thereby allowing proteins to be separated by molecular size. The electrophoresis lasts between half an hour to several hours, depending on the voltage and length of gel used. Being a small molecule, the bromophenol blue dye is totally unretarded, and therefore it indicates the electrophoresis front. This is the gel running, and you can see the bromophenol blue dye has left the stacking gel. When the dye reaches the bottom of the gel, the current is turned off and the gel is removed from between the glass plates and shaken in an appropriate stain solution, usually Kumasi Brilliant Blue, for a few hours or overnight, and then washed in a distain solution overnight. The distain solution removes unbound background dye from the gel, leaving stained proteins visible as blue bands on a clear background. You can prepare the protein Kumasi stain using Kumasi Brilliant Blue R250, methanol and glacial acetic acid as shown here. Distain solution contains methanol and glacial acetic acid without the dye. Now let's see how we can estimate the molecular weight of protein separated onto the SDS-PAGE gel. Because the principle of this technique is the separation of proteins based on size differences, by running calibration proteins of known molecular weight on the same gel run as your unknown protein, the molecular weight of the unknown protein can be determined. Here you can see the top of the resolving gel, the dye front and unknown protein bands. To determine the molecular weight of an unknown protein, the relative mobilities RF of the standard proteins are determined. Using a ruler, you can measure the migration distance of unknown protein, dye front and standard proteins in the marker. Relative mobility RF can be calculated as distance migrated by protein divided by distance migrated by dye. Once you have values, then you can plot the RF of standard proteins and unknown protein in a graph of log molecular weight versus RF. Let's see the example of the graph. Once you have plotted log molecular weight versus relative mobility of standard protein bands and unknown bands, you can generate the equation y is equal to mx plus b and solve for y to determine the molecular weight of the unknown protein. As you see here, once you get the value of y as log molecular weight, just calculate anti-log of that value and you have the molecular weight of the protein. I hope you understood the basic principle of SDS-PAGE. If you have any question or you want to give feedback on my videos, please feel free to comment. That would be very helpful. And also check out my website proteomicsmadeeasy.com for more videos. Thank you for watching.